All right, thank you. My name is Helena, and like you said, I am presenting on the effect of an external magnetic field on the Hall effect of a dusty plasma tornado. Before I begin, I'd like to say thank you to Dan Lathrop, my advisor, as well as Sarah Burnett, my grad student advisor. This really would not have gone well without you guys. Do I have the clicker? Oh, it's right here. Thank you. So before I begin, I'd like to preface this by saying that there is no experimental precedent for this kind of work. We have been taking this kind of experimental design from a lot of different ideas and theories, mainly the theory of granular electrification, which is the process by which granular material interacts and exchanges charge in a system, and it transports that charge throughout that system. That, coupled with the idea that the Lorentz force, collisional charging, and the Hall effect can all contribute to charge separation over large scales. This leads us to our main questions of how does an applied magnetic field affect the voltage fluctuations that we see in our apparatus, and is there any kind of way to characterize this kind of stochastic discharge that we see? In order to approach this problem, we first use polystyrene particles, which we then agitate in a cylindrical annulus vertically against gravity with wind. We use polystyrene particles because they are lightweight, they exchange charge very well, and they're very easy to manipulate. We then pour them through this cylindrical annulus in between the center cylinder and then the outer cylinder. One of the main parts of my summer was redoing this entire orientation of these magnets that I have. So we had these 2-ton vertically aligned magnets, and the original setup actually had these magnets aligned like so. And due to the nature of my apparatus, I have this cylindrical annulus, which needs to be presented vertically. So a lot of my summer involved reorienting these magnets horizontally so that I could insert them there. This resulted in a 0.62 Tesla magnetic field, which is the largest ever recorded in our lab. With this new kind of experimental setup, we then insert our cylindrical annulus into these magnetic rings, and then we align them with the dipole. Then we go ahead and we ground that inside cylinder to the fan in order to reduce the noise of our overall apparatus. I then inserted a copper tape electrode on the inside of the outside cylinder. This allowed us then to take the voltage difference across this entire apparatus. Looking at the time trace of the voltage difference coming off of the copper tape electrode, we see a time trace from the oscilloscope directly. We can then analyze this time trace looking at the probability distribution of the amplitudes. But what it is the log of this time trace histogram, which provides us with a much more interesting graph. We see a heavily tailed or heavily skewed distribution here. And what this tells us is that events occurring up to 5 standard deviations away from the mean occur at a probability which is non-negligible. This means that random fluctuations or turbulence are major players in this system. We went on to analyze the system by taking the fast Fourier transform of this data. And looking here, you see a lot of spikes, which are characteristics of background noise. So we went ahead and ignored that. And we took the log-log plot of this. And what we end up seeing, actually, is an f to the -2 characteristic slope of this region here, which we went ahead and analyzed. And it turns out that this has, this has characteristics of diffusive Brownian motion, which is interesting because that then has applications to a random walk of sorts. And the way that we have been theorizing about this is that as you have different polystyrene particles with charges of all sorts coming in and then interacting with that copper tape electrode, you've got a positive charge depositing its charge onto the electrode, resulting in an upward spike. And then a negative charge depositing that charge, resulting in a downward spike, which can then be modeled by using this random walk. So in conclusion here, we have results that suggest that stochastic fluctuations are greater than the Hall effect in this system. We then have a logarithmic probability distribution of the time trace of voltage measurements which show a heavy-tailed distribution, suggesting that random fluctuations dominate the voltage output of this apparatus. And finally, we have a log-log plot of the Fourier transform, which reveals a slope of -2, which is characteristic of a random walk and suggests diffusive Brownian motion. And with that, I would like to thank the NSF for funding me, the University of Maryland for having me. I'd like to thank Dan Lathrop again, Sarah Burnett, and as well as the entire machine shop for helping me move my magnets.